Okay, let's start out, you guys. Welcome back, everybody. Let's just spend a little bit of time going through some more examples, and I'll kind of talk about I did make a mistake on the board. I did include that in the lecture. If you watch the video, 2 times it came up and it tells you where the mistake is. Does anybody know where my mistake at board was last time? Glancing at your notes, you might go, I did, for this problem right here where we were doing this, I forgot to write the sampling distribution inside my integrand. There was no x tilde, no forecasted value. I'll clear that up for you. So, one person noticed. So, again, it just kind of means that probably you guys are lost in the weeds as just to what your distributions are, what's going on, you know. Where do you get this data from? What does all this mean? And then you're like stumbling around the calculus. You just keep practicing these examples and you'll get used to it. This is all pretty cookie cutter stuff, you know. I don't usually see data that I just think it's Poisson. It's usually some mixture, some big mixture of something, and maybe there's Poissons, and I use these distributions as building blocks for everything. And so usually it's not so simple that I see data and it's just Poisson, you know. So anybody that's ever worked with count data oftentimes see like an inflation of zeros or something like that. And so you need to handle that differently. Poissons are kind of interesting because they set the variance equal to the expectation. So this is a counting process. It models a counting process. So lambda is positive. It's kind of the rate, and it's going to control the mean of everything. So lambda is positive. Expectation of x given lambda, I usually write it like that, is lambda, and that's also equal to variance. And so let's just talk about this distribution for a while. Just while I'm at it, just look over here. Review session tonight, same place, same time. I will record it and I'll post that. Again, questions are the only thing that make that go. I come in not prepared with anything. I just have my chocolate. So I want you guys to ask questions so that I can tell you all about everything I know and what's important, what's going to be on the test, and if there's any sort of extra stuff that you want to know about. That's what the review sessions are for. Once we go through some of these examples, I'll tell you what I know about intervals, constructing intervals. Pretty straightforward. So back to Poisson, counting process. Binomial is also counting process. I will distinguish it. It's a coin flipping process that's counting the number of successes you see in something. Probability is P for each one of those coin flips, and you're counting how many successes you see out of that. That's binomial. It's constrained between 0 and n. So there's this pre-notion that you know how many times the coin can flip. You know how many times you've gone out to try to observe something and either it happened or it didn't. Poissons are very different from that, but there is a relationship. So I will say, as n goes to infinity, and simultaneously p goes to 0. Now these have to go in particular rates. So I'll write this down. There is a connection between these two distributions. Probably some of you remember that. But as n goes to infinity and p goes to 0, that's from a binomial model. So now we're getting off to infinite counts. Something happens rarely such that np goes to some value that's not infinity and not 0. So it converges in on something. So the rate at which this happens, it does it such that this product converges to lambda, some number. That will be a Poisson. So then x's are coming from a Poisson with parameter lambda. So sometimes we like to think of these as rare event models. So think about maybe car crashes at an intersection of a road. I'm not saying those are Poisson. I'm not saying that they're independent. I'm not saying anything about that. This makes a lot of assumptions about the nature of things, and you would need to check it. One thing you can always check if you're counting things as you can see empirically, if I just look at the average of my data and I compute the empirical variance, if they're not close to each other, it's not Poisson. Now, in real data, you would never see them being exactly equal. So they need to be relatively close to each other. Why is this a reasonable assumption in counting models? You ever think about this? Like, what does that mean? Is that really how counting processes work? I'm going to argue yes. That basically, the variance, at least I'll argue, the variance increases as the count increases. Why is that reasonable? So if you just think about it like that. Let's imagine I have a barrel, and it's filled with apples. And my barrel is really small, and it contains 4 apples, 4 to 5 apples, something like that, maybe 3, 4, or 5 apples. I've got this small little barrel. I can go in there and say, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, pretty easily. I can eyeball that, and I'll probably be right. So my error in that counting process isn't going to be very big if there's a small number of things that I'm counting. So usually when we go ahead and count things, as we start counting higher and higher numbers, we start making bigger discrepancies. So if I had a huge barrel of apples, then if I went through and I counted them all, my error would be somehow dependent on how big that count is that I'm counting. And we've all done this. So you start counting stuff and you lose track. You're like 2,420. Oh no, I lost count. So, well, it's somewhere around there, keep counting. And so that's the idea. I will argue that if your variance were smaller than your expectation, that's definitely not Poisson. And it's nothing like it. What it probably is a mixture of Poissons. And so it actually violates a fundamental exponential theorem, exponential family property, that variance has to be at least as big as the expectation. If you think that the variance is much smaller and you have big counts, I bet when you plotted that, you're going to see modes of things. It's not going to look like Poissons kind of look like this, where there's kind of a hump in there, it's centered at lambda, the variance has something to do with it. If you ended up seeing that the variance was much, much smaller than your actual counts, I'm going to guess your data looks like this. And you have mixtures of Poissons. So just stuff for you in the future. We'll be dealing with mixture models soon. I'll be walking you through how you actually deal with these cases. Again, we're just going to deal with the simpler problems up front. Once you can do this stuff, you can do everything else. Okay. Oftentimes the variance is much, much larger than the mean of that. And there is a distribution that I know that has the variance being higher than the mean, and that's a negative binomial. And so I can tell you what a negative binomial looks like. It looks like this distribution. I'd like you to go study these things. If you haven't been in probability class recently, you can kind of write down, there's a lot of parameterizations to this, but negative binomials. Look like, and I'll use this parameterization, n minus 1, r minus 1. I'll tell you what these things are in a second. P to the r, 1 minus p to the n minus r. Kind of looks like a binomial, but has a relationship to that. It's really the question of how many coin flips do I need to flip to see 5 successes? So let's just remember what a binomial does. I'll go back to this in a second. Binomial says how many successes given a fixed number of coin flips. The negative binomial is a similar question. It answers how many times do I need to flip the coin before I see a fixed number of coin successes. That's a different thing. So this is going to be the trial of the rth success. thing that you're plugging in for how many successes you're looking for. So this is the random variable right here. And this is the probability of success or no success, just like in a binomial model. So very similar. So I'll just write this down that this is Fn R. And there's different ways you can parameterize it. You can say, how many total trials do you want before you see it? And that's the way I parameterized it here. And sometimes in textbooks, they'll say, how many failures do you see before you see R successes? They're totally related to each other. The number of failures plus the number of successes R is the total number of trials. So just keep in mind, people use two different parameterizations, and they're just off by a shift. This is what a negative binomial is. In negative binomials, I'll let you play around with this, have higher variance than their expectations. We'll see that in this example in a moment. We'll use some of our tools that we've already learned, iterated expectation, iterated variance, to figure this all out. Yeah, it's exactly that. So that's exactly what it is. So geometric distribution is how many times do I have to flip a coin before I see a success? And so Jenny wants to know about two successes. So it's the sum of two negative binomials. So negative binomials are sums of geometrics. Very good. Those are the connections you want to be able to make so that you need to know less distributions. You know how they're related to each other. Okay, so that's what a negative binomial is. So I think this is a reasonable assumption, but oftentimes I'll move over to a model that looks like this. Right here, if I think the variance is higher. If I think the variance is lower, I usually use mixtures of Poissons. I'll teach you about mixtures later on. We might use Poissons, we might use something different. Let's just work through this. I'm not going to do all the work for you, but I'd like you to do some of this, but I'll fill in the details. Or I won't fill in the details, I'll tell you what the answer is. So, Poisson prediction. I always want to know, like, where did the names come from? Where are these things? Does anybody know why it's called a Poisson distribution? Does anybody know what Poisson means in French? Fish. Has nothing to do with fish. It's a person's name. So, and Poisson gets this distribution attributed to them. Usually what I know about things is whoever the name is, whoever gets the name for something didn't come up with it. So I think he described this. It wouldn't surprise me if there's somebody else that came up with the distribution at a different time, in a different place. People won't go to war over that. But Poisson gets this one and nobody ever argues with it. The distribution looks like this. Right here. So that's a mass function. So this is a discrete distribution. So all the things you always want to remember in all of this is where do the x's live? Where do the parameters live? Make sure you know those things. You probably know the expectations and the variances as well. So Poisson prediction. So we want to forecast x tilde given x. How do we do that? Same thing Bayesians always do is we average over our uncertainty. If we had model uncertainty, we could include that, but we're assuming, at least in the early part of this class, we know what the models are. So this is just integral from 0 to infinity. This is going to be f x tilde given lambda multiplied by the posterior distribution that I've learned through previous data draws. So I got an interesting question last time. Where do we get the data from? Where does that actually come in? Some scientist came to you with it. You've collected it. You've observed it. So there's data everywhere. So you get it somehow. People walk in with these crazy data sets and you have to start figuring out what kind of models look like that data. So in my class, we get to presuppose is just coming out of here. Usually I have you do simulation studies so you can verify your answers. We don't work with real data in this class. So apologies on that part. But data comes from a Poisson distribution. And so I think I know how to do all of this. So this is just going to be integral. This is going to be my Poisson distribution. So e to the minus lambda. Lambda to the x tilde over x tilde factorial. And then I'm going to multiply by my posterior distribution. So that begs a question, what's the prior? And I think we answered that last time. So with a gamma prior, so let's use a gamma alpha beta prior. Why? It's conjugate. There's better reasons than that. So I'm still going to have to pick alpha and beta at the end of the day. Good defaults for that are 0 and 0. We'll see that later on when we study Jeffrey's prior. Yui came up to me and he said, well, if you're going to treat that as a scale parameter and place the prior 1 over lambda, which is a gamma 0, 0, you wanted to know much more about that. So if you want to know more about that kind of stuff, you can ask. So I'll give Yui a better answer than I gave him at the end of last time's class, after this class. Review sessions will go for that stuff too. So under this, right here, I know that this thing is going to be gamma. I just kind of need to work through that distribution. I guess since we haven't done it, we can do it. I'm going to write down this distribution. Just hold it at the top. P to the R, 1 minus P to the n minus R. We'll see this in a second. Turns out this is a negative binomial distribution. And so somebody asked me at the end of last class, how do I know that? I wouldn't know that. And I couldn't just stare at it without working through the details. So I wouldn't have had any idea that that was true, you know, when I was first taking base class. Okay, so let's just write down what posterior looks like. Lambda given x. This is going to be proportional to my likelihood function. I goes from 1 to n, e to the minus lambda, lambda to the xi, over xi factorial. So that's my likelihood function. And then I'm going to multiply this by my prior. So here's my multiplication right here. I'll multiply this thing by my prior distribution. That's going to look like, I've got it on lambda, so this is going to be e to the minus lambda beta, lambda to the alpha minus 1. And I haven't normalized anything. So this is my gamma distribution. For my prior, this is my likelihood function. I'm just producting up the sampling distribution, plugging in my data, and then thinking about it as a function over the parameters, the likelihood function. And so what does this look like? This product runs over e to the minus lambda, so that's e to the minus n lambda. And I've got another e to the minus lambda right here, so I'm just going to combine those. This is e to the minus lambda n plus beta, my hyperparameter. And if I were doing my default reference analysis that I'll tell you about later, beta would be 0. And then I've got this lambda right here, and it's going to combine with this thing right over here. So this is going to look like lambda to the sum of the xi's. So when I take that product over the sum of the xi's, it appears right there, plus alpha minus 1. And I leave that minus 1 always dangling so I can recognize what distribution this is. And this thing right here is a nuisance. So if xi's are relatively high, you won't be able to compute that very well anyway. So if the xi's were like 100 or bigger, it'll crash your computer to try to compute that number. And so it's like 60 or something that you can compute in double precision. So nice thing about Bayes is I don't need it. It doesn't have the parameter in there. So what a computational savior. You know, I can just write everything up in proportionality. So this thing right here is a gamma with parameters, sum of the xi's plus alpha and plus beta. Let's just do a sanity check and think about our answer for a moment, like we spent a lot of time in the past. What's the expectation of this thing? Posterior expectation for a gamma is this thing over that thing. I usually call this alpha tilde or something like that. And we usually call this beta tilde. So for a gamma, it's alpha over beta. Alpha tilde over beta, in this case, it looks like this. Sum of the xi's plus alpha over n plus beta. Big surprise. It looks like a mean. And if I pick my default choices, alpha and beta are both 0, this is x bar. So this is converging to x bar. I think that answer makes sense. So if I were to try to guess where the center of my process is, it's going to be this thing right here. The posterior predictive distribution is not going to change that. It's going to be centered at the same place. And so if you want to try to mentally validate that for a second, you can work through the iterative form. If you don't want to do that, I'll do it for you in a moment. So kind of makes sense. A Bayesian is telling you a lot more than this. They're telling you the variance. They're telling you what the whole distribution looks like. So I don't think that this is super compelling why you want to be a Bayesian and you just come up with this regularized estimate of the mean, but rather we're going to describe all the uncertainty in this parameter lambda through the posterior distribution. And for forecasting, we're going to integrate over all of that. We're going to use all that information. I think that's a good idea. So instead of like taking this and just shoving it in right there, I'm going to integrate over all its uncertainty. And that's where a Bayesian can really win, is integrating over uncertainties. And when you have a lot of parameters and models, that can become a big deal. Okay. So on to our calculation. I'm going to plug in this gamma. And in this problem, it's a little bit cumbersome. To recognize that everything's a negative binomial, you probably need to carry all of your normalizing constants. So I'm going to do that, and I'm going to tell you what the answer to this integral is in a second. So I'm going to write down all of my normalizing constants. So this is going to look like beta tilde to the alpha tilde. So that's going to look like n plus beta to the alpha tilde, that's sum of the xi's, plus alpha over gamma function of sum of the xi's plus alpha. Again, these are all normalizing constants, but to recognize this form, you're going to need these. And that's how I would figure out what this thing is. So then I've got lambda to the alpha tilde, so that's sum of the xi's plus alpha minus 1. And then I've got my exponential bit. So that's e to the minus lambda n plus beta. Then I'm going to integrate over all this. We'll come back to these ones in a moment. So again, this is really just review, just a new distribution so that we get into the flavor of what does Bayesian do. So this is my posterior distribution. I've written it down into its full glory. And this is my sampling distribution. And that's where the x tildes show up. You cannot throw this x tilde away, this one right here. You have to hold on to it because that has something to do with your distribution. I could start chucking things. I can't chuck that because it has to do with what I'm integrating against. But I could probably get rid of these things. But I'm going to suggest you hold on to them. Otherwise, you won't recognize the solution. Keep in mind what you're going to be integrating over. I'll just write it. We'll factorize everything out. You're going to have n plus beta to the sum of the xi's plus alpha over gamma function sum of the xi's plus alpha. These things I can factorize out. I can factorize that one out right here. X tilde factorial. And then everything else involves lambdas. E to the minus lambda. I've got a lambda to the sum of the xi's plus alpha minus 1. And there's another e to the minus lambda n plus b. d lambda between 0 and infinity. And maybe I'll compartmentalize this a little bit more and I'll get rid of that one right there and I'll just add it in right here, plus 1. I kind of like that the n plus 1 is showing up. It should be like that. I'm forecasting uncertainty about n things I know that's going to help propagate my uncertainty. And then I have this extra thing that's showing up. Gives me a little bit of comfort anyway. And so this just looks like a gamma kernel. So this is a gamma with parameters, sum of the xi's plus alpha, and then n plus b plus 1.
Where is the lambda to the x tilde?
Yeah, we've got to have this one. Very good. Thank you. X tilde. Awesome catch. So it's in there. But yeah, absolutely. You've got to keep track of those things. Can't throw that one away. So we've got everything. So this is equal right here. So this looks like I've got an x tilde in here as well. And if you don't see x tilde in all of this, you probably know you're making a mistake. So great catch. And so I know how to come up with this right here. So this is just going to be, this whole integral is going to look like gamma to the sum of the xi's plus alpha plus x tilde over n plus beta plus 1 to all of this stuff. Sum of the xi's plus alpha plus x tilde. I'll write this down a little bit neater. But that's what my answer is at the end of the day. Let me write down in a simplified form what this looks like. Question?
That's the inverse of the normalizing constant?
That's the inverse of the normalizing constant of a gamma. So I just did that all in one step and just flipped it over. And so that's kind of what I'm getting at. Like this should almost be autopilot if you know your distributions. So you get to see me up here looking like I'm on autopilot, and all I'm doing is knowing what the integrating constants are of distributions. Looks a lot fancier than it is. So yeah, just study that stuff and you'll be able to do this as well. So at the end of the day, you come up with this. And I'm just going to simplify everything. I wrote it down this morning. So this is going to look like gamma x tilde plus sum of the xi's plus alpha. This is going to look like gamma function sum of the xi's plus alpha. You can see all those terms over there. There's going to be an x tilde factorial as well. And this is going to be multiplied by this thing, n plus b. So there's a little bit of compartmentalization of everything I wrote over on the other board. This is going to be sum of the xi's plus alpha, 1 over n plus beta plus 1 x tilde. So let me just ask a question. Does this look familiar? It looks like that thing up here. So 1 minus this thing right there is that. You can work through that. You can see your number of successes and your number of failures. So here's your number of failures in some sense your number of successes. But I don't think about it this way. I just think it's a negative binomial. So I don't really cast this into this, like, how many successes, and those are the number of successes. It's just a distribution, in this case, of my forecasted value given everything else. Negative binomial pops up. And the way I would interpret this is it's got this shape, whatever it is. And it's a function of x tilde. So it's a little bit complicated to see. And then maybe I would characterize the expectation and the variance for somebody. If I didn't know those expectations and variances of negative binomials, I do, but I always know them through the iterative forms. Then I would solve them using those forms. Lots of ways to know things. Let's just work through the iterative forms and see what the expectations are. So you could try to do that from scratch and work out the expectations of the variances. But I did learn something really important in this exercise carrying through the whole integral, that a scale mixture of Poissons with gammas is negative binomial. So I just learned a new fact, and that's true in general. So if I mix a Poisson over a gamma, that's that integral we just solved. That's a scale mixture because lambda is acting as a scaling parameter. It's a negative binomial. So now I know a new connection. I know scale mixtures of Poissons are negative binomials, and they have something to do with each other. Let's just look at the expectation. X tilde, given everything else, iterated expectation. This is going to be x tilde given lambda. I'm going to condition on that parameter, cap x. And then I better condition on cap x as well. Everything's conditional on our data. That's what we get to know. Expectation of x tilde given lambda and the data. I know the expectation of that is conditionally independent of this because I get to know the parameter. So that's lambda. So anytime this is the posterior at the end of the day, you don't shift the mean. That doesn't always happen, but it's common that they're centered at the same locations. And so I know what this is. This is going to be my posterior expectation. We wrote this down a couple minutes ago. Xi plus alpha over n plus beta. So I could write this down. I've got this negative binomial distribution. I forget what the expectation is, but I can solve it using this other tool in our toolbox, and I can do that really quickly. The more interesting thing is probably the variance. So the variance of x tilde given my data, this is going to be equal to the expectation of the variance of x tilde given lambda and x. This will be conditional on cap x as well. I'll write that in as a reminder, and I add it to the variance of the expectation. X tilde given lambda x given cap x. And I need to work this thing out. So this is going to look like the expectation variance of a Poisson is lambda. I know what this is. This is Poisson distributed, conditionally independent of the data again. So this is the expectation of lambda given x plus the variance The expectation of x tilde given lambda is lambda again. Still a Poisson at that layer. It's this, right here. So my expectation of lambda given x, again, we know what that is. I just wrote it down. Sum of the xi's plus alpha over n plus beta. And then I have this other term right here. This is the posterior distribution for lambda. And I know what the variance is for this posterior. That posterior is a gamma distribution, so lots of layers. But I know what the variance of a gamma distribution is. Somebody tell me it's not Warren what the variance of a gamma distribution is. Good job. Knowing all your, if you would like to, you can. What is it? Very good. Yeah, exactly. And the parameterization I work with is alpha over beta squared. So this is sum of the xi's plus alpha over n plus beta squared. You can factorize out the sum of the xi's if you would like to and see how this relates, but you'll notice this expectation and that variance are not the same. This is a negative binomial distribution, and negative binomials always have inflated variance. And that makes sense for forecasting, is that it needs to be greater than the variance you saw just from your posterior. It's gonna grow because there's this extra layer to it. Yes, please.
Shouldn't the alpha be outside of your sum? Because sum of the xi's?
Yeah. I'm not sure why I did that. Thank you. Supposed to be clear. Yeah, it annoys me too when people don't write down their braces on summation signs. I never know where it ends. Thank you. I had that wrong. So this is just a tidbit, another distribution, and basically on the first midterm, or the only midterm, I'm going to ask you questions like this. And I'm going to consider these easy questions. You should just be able to carry them through. If you want practice, just work through every distribution that you can think of. And you'll already know what my example looks like. Okay. So that is a negative binomial. New distribution. How do I always figure out what the negative binomial looks like and what's its parameterization? I always do this. So I always think of it as this scale mixture with a Poisson. Okay, you can take Poissons, and I can have other scale mixture. Lambda can follow some other process. It doesn't have to be gamma. It just needs to be positive. And I'll create another counting distribution out of that. So that's kind of cool. So Poisson mixtures with gammas are negative binomial. Poisson mixtures with some other crazy distribution is some other counting process. And that's how I go about business. So usually it's like, well, that doesn't look right. I'm going to grab some other distribution and wiggle it around until I can match my data. So that's what modelers do. So lots of neat stuff once you start understanding mixture representations of distribution. Very useful. Okay, last time, I'll say this. From last time, I made a mistake. Just want to fix this up. We looked at xi's were coming from a binomial distribution, and pi goes from 1 to m. I'll switch my notation right there because I've already used n. I might assume that p itself comes from a beta. I have some flexibility in how I choose that beta. If nobody told me anything, I would probably use a beta half-half. We'll have more good reasons for understanding that once we get into Jeffrey's priors, the reference priors. So I know what the posterior distribution looks like. So P given X is going to be a beta. We've done this a whole bunch of times. We played around with this on the homework. This is going to be sum of the xi's plus alpha. This is going to be n. This is going to be I goes from 1 to m right here. This is going to be nm minus sum of the xi's plus beta. So that's my posterior distribution. When we went to solve the posterior predictive distribution for this, I forgot to write down the first part. I just threw the posterior in here. So integrate between 0 and 1. What I need is the original distribution. So I forgot to write this down. This is n, choose x tilde. We can't get rid of that. So this is going to be p to the x tilde. Can't get rid of that either. 1 minus p to the n minus x tilde. And then I have my posterior distribution. I probably could get rid of this part right here. So the normalizing constant, but I guess I'll write it down. This is going to be nm minus sum of the xi's plus beta. This is going to be beta to the alpha. I'm just going to write this down. Beta function of sum of the xi's plus alpha nm minus sum of the xi's plus beta. I need to invert this thing. If you want cleaner notation, you really can't have it. You can write it down as a beta function and describe that. You can write it down as gamma functions. But they're integrals unless you know alpha and beta were integers. Usually I don't work with integers there. You'll notice that there's a connection between gamma functions and factorials when the argument is an integer. So gamma function of z is z minus 1 factorial, if z is an integer. Some of you might know that. And then this is going to be p to the sum of the xi's plus alpha minus 1, 1 minus p, nm minus sum of the xi's plus beta, and there's a minus 1 in here, dp. So messy thing, last time when I wrote this down, I forgot that. So make sure you don't do it. If you don't know what any of these distributions are and you don't know how to work through the integrals, you can always do that Monte Carlo thing that I told you about. You'd still be able to forecast. You'd probably have less insights if you knew something about your distributions. But for Bayesians, forecasting is always the same thing. The same process over and over again. So I did write some other distributions on the board at the beginning. You're going to be working through higher dimensional normals in the future. I'll just tell you as a heads up, if you didn't know cap sigma in a multivariate normal, and you integrated it through, and I'll walk you through some of those details when we get back from break, you get a multivariate t. And I'll tell you about multivariate t distributions later. I want to take the last 4 minutes and tell you about intervals. It really doesn't take much time. So I'll say, I'll probably pick up on Monday. Just as a reminder, we don't have class on Friday. All break. Probably pick up with HPDs, but I'll just draw you a picture of what they are. So intervals. So Bayesian intervals. For Bayesians. Write that. Intervals for Bayesians. Usually we call these credible intervals. And these are belief intervals. So Bayesian posterior distribution is telling you where they think the parameter is. It's a probability, you can compute probability statements about where you think that is. So for Bayesian, a 95% interval, regardless of how we construct it, is a belief interval of where we believe everything is. Of course, in something like a continuous distribution, I can kind of combine 95% mass in lots of different ways. So let's just look at an example. So if I were doing something like this, let's say I have a distribution and it's symmetric, I could combine something like this. I could create an interval that looks like from that point out and that point out, and maybe the area under this curve right here. So I have everything but the middle section. If that's 95%, this interval that I've just constructed from here all the way out, here all the way out, is a 95% credible interval. If somebody came to you and they gave you this interval, what would you think? It would drive me crazy. Yeah, it's a belief interval, but I would say you just missed the most important parts. You know? So this is your most likely stuff, most probabilistic stuff in a Bayesian sense. So you wouldn't want that interval. So you probably want to contain the mass of the distribution. So this is a bad interval. You could just collect 2.5% in the tails and then grab the stuff in the middle. But if you had a skewed distribution, that probably wouldn't describe things accurately well either. And you did that maybe on your homework when you were studying the coverage intervals from the Bayesian posterior. If it was relatively concentrated, so that's not too bad. What Bayesians really want and everybody wants these, is the shortest intervals. And that's the same as saying, I want the highest density intervals. So I would argue this is a bad interval to construct, even though it would be a 95% if I added up mass to 95%, because it doesn't have the densest region. It's a lot of density right here, a lot of posterior mass. So what we want are the highest posterior density intervals. And next time I'm going to teach you a little illustration on how to get those intervals. So I think we'll come back next time. We'll talk about highest posterior density intervals, but even if you're a confidence interval person, and you're doing this, sort of coverage thing, people usually try to give you the shortest intervals. And so in Stat 101 classes, we're a little bit sloppy and we don't teach you how to do that. But in general, you want your shortest intervals. I like the Bayesian thing, because our intervals, I can say where I believe P is. I can maybe calibrate wherever the parameter is. And maybe I can calibrate it in a frequentist sense, and I can maybe have both things. Maybe it covers a certain amount of times. Maybe I can beat an asymptotic frequentist, but I also have interpretation as to where I believe the parameter is. And I can construct the shortest points. So next time, on Monday, when we come back, I'll tell you all about those, and then we'll start moving into higher dimensional analyses. I think that's it for now, you guys. So have a great break if I don't see you tonight. And I'll start handing out the homework. Thank you. Let's give it a minute.
Question.
Hands